Hey there, can folks hear me okay? Wonderful, wonderful. Okay, so we are going to see how well a completely remote class session can work. We'll have to see how that goes. I'm going to try to keep my chat window up so that I can see questions that are coming in. Do please feel free to ask questions as we go along, and I will try to address them as we do so. So let me start with some logistics and some announcements. The logistics for this week. The only assignments that are due this week are going to be homeworks. My recollection is that there are two separate homework assignments that are due. If anybody remembers which ones they are, and you post it to the chat, that would be great. They are 11 and 12, Ashlyn says, so thank you very much for that. My recollection is that both of those are relatively short compared to some of them that you've been seeing before, so the overall homework workload is not going to be all that huge. I am in the process of writing the fifth small group activity, which I will be releasing, I hope, middle of the week, Wednesday, maybe Thursday, to have it due sometime next week. I may make it due a little bit later next week so that you have some extra time with it. The plan for the exams that are coming up is that the fourth midterm exam I will be releasing on the Thursday of Dead Week, and it won't be due until the end of finals week. The three portions of the final that we will be doing will each be released on the Monday of finals week and will be due the Friday of finals week. The three parts are going to be separate, so you can take them individually as you wish. Don't forget that you are able to use redemption points from those final exam portions to bring up your midterm exam grades to higher grades if you score a higher, percentage on that portion of the final. Question from the chat. So the final and midterm 4 are different. Yes. So initially, my philosophy had been that you should have two opportunities to show your understanding of the material for each bit of the material, one of them on a midterm and one on the final. I realized that for the fourth midterm set of material, that doesn't make a lot of sense because there is no time gap in between the fourth midterm and the final. So I am not going to have a fourth midterm portion of the final. You'll just be doing it once, doing the fourth midterm material once. What I will do is take the fourth midterm grade, that will count as the fourth midterm grade. I will then cut it in half since each portion of the final is out of 50 points instead of 100. And that fourth midterm grade will also count as the fourth portion of the final. There will only be the three other portions of the final. The final portions will each be only an hour long, and so they will be significantly shorter than the midterm sections will be. The midterm 4 is due Friday as well. Yes, so there's a policy that says that there can be no exams that are due during Dead Week, and so I figured there's no real point in making the fourth midterm due any earlier than the end of finals. So you will have one midterm that is due on the Friday of finals and 3 segments of the final that will be due at the end of finals. So we could technically take the final and take the redemption points from midterm. No, so there is no fourth portion of the final. There is only the fourth midterm for that set of material. And so no redemption points go along with the final, with the fourth midterm. The fourth midterm will count in two places. It will count as your midterm, and it will count as half of its points will count as the fourth portion of the final. Okay. Everyone clear on the logistics for the midterms and the finals? The final midterm and the finals? All right. Okay. Are all the three other parts of the final mandatory? Well, I mean, if you want points for them, yes. So redemption points only works one direction. It only works in the direction of you take the final and that can increase the score of the midterm. It doesn't go the other way around. So if you want points on the final, you take the portions of the final. Okay, so as many of you saw on Piazza, there were some issues, some significant issues with cheating on midterm number 3. What happened was that it looks like at least 2 students posted questions from the exam directly to Chegg, and there were Chegg answers that were up. And many students in the class went to those answers and at least looked at them, and in many cases used them. I am going to point out that quite a few of those answers that were posted on Chegg to those questions were in fact wrong. And so one of the pieces of information that I have to work from is that if the incorrect answers on an exam match the pattern of incorrect answers on the midterm exam, then that is a pretty strong, on Chegg, then that is pretty strong indication that somebody used the answers from Chegg. In addition to that, I am in the process of getting from Chegg a report of who posted the questions and also who accessed those particular pages that had the questions posted. I have talked to many students about this problem already, and we are in the process of implementing the university mandated sanctions for this kind of behavior. So so far, I have only been talking to students that have come forward to me about this particular issue. It matters if students come forward or not. Students coming forward are treated as having demonstrated some honesty in the situation, which matters in terms of what the sanctions are that get imposed. Students that do not come forward, but where evidence does show up that they were there, are not going to have as generous of sanctions applied to them. They will end up being more severe. So I recommend that if any of you are in this boat and have not yet come forward, that I recommend that you do so before I get this report from the Dean of Students office and from Chegg on which students were using this service. So I do need to, I feel like I need to make a few things relatively clear here, because I've said that you are able to use outside resources. The distinction that we make, that is made for my class, is that if you look up similar questions to the ones that are on the exams, you learn from those examples how to do the work, how to do the problem, and then apply that new understanding that you've developed to the specific problems that are on the exam, that's fine. So going to Khan Academy, going to other sites that have worked examples, that is perfectly fine to do, because that is you learning something and then taking the opportunity to use to demonstrate that understanding on the exam. The difference, the place where it's a problem is when someone is looking at someone else's answer to a specific exam question, because that has the potential to to have someone not doing the thinking process themselves, and that is a disallowed process. Now, I'd like to talk about Chegg specifically. Chegg has been gaining a reputation nationwide among faculty for being a hotbed of cheating. This is because they are a subscription service, a paid service where students can post questions, very often from homeworks or from exams, and their experts will attempt to answer those questions for you for this fee. They will occasionally send around emails saying, don't do that, but their business model is designed around people paying a subscription fee for this service of getting questions answered directly. It is absolutely possible to use Chegg in a fully honest way. However, because their business model is designed the way it is, in a way that actually encourages cheating, nationwide it has it has been developing this reputation of being a hotbed of cheating. My understanding is that there is a committee at BSU that is working on a university-wide policy associated with Chegg, and my understanding of the current state of that policy is that they are going to be recommending a complete ban on its use for students on campus. Whether that policy does end up happening or not, I know that there are faculty across the university and several faculty within the chemistry department who feel so strongly about Chegg being a source of cheating that many of these faculty view even having a Chegg account as evidence of an intent to cheat. I am not in that, I am not a person who has that particular attitude myself, but I've talked to enough other faculty to know that this is a growing feeling among faculty members. And so my recommendation, this is a personal recommendation, is that it is not worth having your name associated with Chegg. There are other services that provide many of the same functions that are legitimate from Chegg out there, such as Khan Academy, such as a variety of YouTube channels that look at work through example problems. There are legit services out there. Chegg is a dangerous one to have yourself associated with, and so my personal advice is it's not worth the risk. Okay, there's a question in the chat. What if one or two questions just coincidentally have the same answers as Chegg, but we did it ourselves? One or two questions is not, in my mind, a pattern of agreement. One or two questions is evidence that something went means I should look a little more closely at it. But that by itself is not sufficient for me to say, yes, this was definitely somebody who cheated. Okay, I'm going to take that as having said all I need to say at this point on this particular issue. Does anybody have any other logistical questions before I get into the content for this week?
Are we going to be having any more group activities / content videos before the end of the semester?
So it does not look as though I'm going to have time to do content videos for the rest of the semester. So my plan is to try to do content lectures live on Monday and Tuesday. They will be duplicates of those so that you only have to show up to one of those two. My hope is to be able to have Wednesdays and Thursdays be Q&A for each of the 2 weeks. If on a particular week I am unable to get through all of the material on the Monday / Tuesday sessions, then I will that will bleed over into the Wednesday and Thursday sessions. But as since each of you are officially signed up to be in either Monday, Wednesday, or Tuesday, Thursday, I will make sure that any new presentation of material will be identical between those pairs of days. In terms of small group activities, I am in the process of writing the fifth one. There will not be a sixth. The fifth one, I am hoping to have released to you guys probably by Wednesday or Thursday of this week. And I will extend when it is due until towards the end of the following week. In the grade projection spreadsheet, what you should do for the sixth the sixth small group activity that is listed is that you should take whatever your high score is and duplicate it and put it into that sixth slot. There's a question in the chat, will midterm 3 be curved? I don't know at this point, because I have been working through all of the, through individual meetings with students on the cheating issue so far, and I haven't had the time to be able to deal with this, with the curve. The grades are significantly higher this time. The mean, I think, is around 45 or something like that, and where I was targeting for a mean to be is around a 50. So it's actually not all that far off. Any curves that are going to happen will be individual based on the grade distributions for that particular exam. I'm hoping to have that figured out early this week. Any other logistical questions?
And then just to confirm, 16.1 through 16.4 and then 17.1 through 17.7 are all going to be on midterm 4.
That's correct.
Okay, so it's
Yep.
10 sections.
10 sections, 2 full chapters. Yeah, so we have 2 topics mainly that we're going to be talking about. This week is going to be entropy, spontaneity, Gibbs free energy. That all is together as one topic area. And then next week is going to be electrochemistry, and that is all one big topic area. And that will be the entirety of midterm exam 4. Okay, let's start diving into some material. I'm going to share screen with you guys. I will hopefully be able to keep up the I will hopefully be able to keep up the chat window so that I can see any questions that come up, and we will start talking about spontaneity. I need to pull up my notes. Here we go. Okay, so main topic this week is spontaneity, and what we mean by that is whether a reaction can happen or not. A spontaneous reaction can happen. A non-spontaneous reaction cannot happen. It's important to remember, though, that can happen doesn't necessarily mean will happen. For example, it's a spontaneous reaction for a diamond to turn into graphite, but the kinetics of that reaction are so slow that it effectively doesn't happen over the lifetime of the universe. So in order to talk about spontaneity, we need to bring into sharper focus a concept we introduced quite some time ago, entropy. At that point, we described entropy as a measure of the disorder of a system, but we need to develop a more quantitative explanation of entropy to really understand what we're talking about. And so to do that, we're going to start by talking about a deck of cards. So a deck of cards has 52 cards in it. And so how many arrangements are possible for a deck of cards? Well, the answer to that is 52 factorial. And so by factorial, we mean we write a factorial by putting an exclamation point. And what factorial means is you take the number, you multiply it by 1 less than the number, you multiply that by 1 less than that number, and so on until you get all the way down to 1. So how big is the number 52 factorial? Well, really, really big. So you see this number here. We are looking here at 8 times 10 to, I'll have to wait until this, my Mathematica file starts acting better. Let me start then by explaining why 52 factorial is what we're doing here. So if you imagine taking this deck, the first card you draw can be any of 52 cards. The second card you draw can be any of the remaining 51 cards. So of those first 2 cards that you draw, you have 52 times 51 possible cards that you could, card pairs that you could get. And so if you're ordering all of the cards, then you end up with 52 factorial, which is this 8 times 10 to the 67th number of arrangements. Now, of those arrangements that we have, how many of them can we consider to be ordered? Well, if by ordered we mean ace through king for each of the suits, I'm going to quit that. If we mean ace through king of each of the suits, then, but the suits may be in any order we want, then there are 24 different ways we could arrange the order of the cards. And so we would take our 52 factorial, divide by 24 to find out how many tries we would need to take randomly shuffled cards and randomly get an ordered version. And so the answer to that is it would be 3 times 10 to the 66th times that we would expect to have to shuffle the cards before we would find one time when the cards are in order. That's a really big number, and it's hard to imagine a number that big, but let's try. Okay. So there are 7.6 billion people on the earth. Let's suppose that each person on the earth has a deck of cards and does nothing except shuffle it. And let's say you can shuffle the deck once every second. How long would it take for everyone on earth to need to shuffle their decks before one of them would randomly turn out to be ordered? Well, the answer you get by doing the math on this would be 1.4 times 10 to the 49th years. The universe itself is only 1.4 times 10 to the 10th years old. So if every star in the galaxy had 10 inhabited planets around it, and each one had the same population as Earth, and everyone on all of these planets was shuffling cards, and if the same were true in every galaxy in the observable universe, and we were all shuffling at a rate not of once per second, but once every nanosecond, it would take 200,000 times the age of the universe to get an ordered deck once. That's ridiculous. It's huge. This is what we mean when we say that it is a spontaneous process for an ordered deck of cards to turn into a disordered deck when you shuffle it. It's what we mean when we say it's a non-spontaneous process for a disordered deck to turn into an ordered deck by shuffling. So it's not that it's impossible in principle. It's that the likelihood of it happening is so stupidly small that we can be absolutely confident that it will never, ever happen. And that is only 52 cards. If we're looking at a chemical system with, say, a mole of molecules, then instead of a number like 52, we're looking at numbers like 10 to the 23rd. So a spontaneous process in these contexts is one where we move from an ordered system to a disordered system. And this happens spontaneously because there are so many more disordered systems than there are ordered systems. We're going to develop these ideas a bit more by looking at a simple system, dye molecules in a glass of water. And we're going to model that as 10 boxes, and each box here is going to be a place that you could put a dye molecule, and or you could put a water molecule in that location. And we are going to call our dye molecules here little blue marbles that we drop into the boxes. And so we can put them in any of the various places in these boxes, like so. And if a box is empty here, then we say that one has a water molecule in it. Okay, so how many different ways are there of arranging these molecules? Well, the first blue marble can go into any of 10 squares. So that's going to be 10. If the second marble can go into any of the remaining 9 molecules. So 9 spots. So that's going to be 10 times 9 or 90 as the number of places that these can go. A third molecule can go into any of the remaining 8 places, 10 times 9 times 8. So this means that we then have 720. So let me type that in here. So we have 10 times 9 times 8 equals 720 possible places we could put them. Except if we put the first marble here, the second marble here, and the third marble here, that's the same as doing it in a different order. First marble here, second marble here, third marble here. So if we look at the possible ways we could do that, first, second, third, first, third, second, and so on, we find that there are 6 different ways that we could have gotten this particular arrangement of this one arrangement of the molecules. And so we have 720 divided by 6, or 120 different arrangements of 3 dye molecules in 10 boxes. There's a question in the chat, where does the 24 come from that you divided the 52 factorial by? That is exactly the same thing as dividing by the 6 here, because there are different arrangements of them. And that 24 came from the different arrangements of the 4 suits. So spade, heart, diamond, club, spade, club, heart, diamond, and so on. There are 24 different ways to do that. So same concept here. So we're going to want to try to scale this up to later situations. And the way this works to scale it up is to say that what we are doing is we are taking, right over here, what we are doing is taking 10 factorial divided by 7 factorial. So what we have here is in the numerator, we have 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. And notice that everything from 7 through 1 cancels, and so what we're left with is the 10 times 9 times 8, which is what we got by saying that, well, the first marble can go anywhere in the 10 boxes. The second one can go anywhere in the remaining 9. The third one can go anywhere in the remaining 8. And then we also then need to divide by the number of ways of arranging. How did I get the 7? The 7 is how many boxes there are that are left. So we want to have what we have here, 10 times 9 times 8. So we need 10 factorial divided by 7 factorial so that all that's left is the 10 times 9 times 8 part.
Professor Alton.
Yes.
Why aren't you using the S equals K ln W equation that's in our book?
We are about to. What we are doing here is determining W. Okay. So we also now need to be able to divide by the 6, and where that's coming from is 3 factorial. So this is going to be 3 times 2 times 1. So 3 times 3 factorial. So our general formula, let's suppose we have n boxes and we have m dye molecules. Then our formula is going to be n factorial divided by n minus m factorial and m factorial. So we have 10 factorial over 7 factorial times 3 factorial. I am going to make this into a formula here. So I'm calling it the microstates formula, which you will, I'll explain what a microstate is in a moment. I'm going to define that, and you see if I put in, if I call this formula with 10 boxes and three dye molecules, I indeed get the 120 that we had before. Can you explain why you divide by 6 instead of multiply? So the idea here is that we have 720 arrangements of putting 3 dye molecules into 10 boxes if they were distinct. If this one was labeled 1, if this one is labeled 2, and if this one is labeled 3. And so in that in this idea of the 720 different arrangements, then this arrangement here, the top arrangement, would be considered a different arrangement from the bottom arrangement. And that's how we would get the 720 that we have here. But we can't tell this dye molecule from this dye molecule. They are indistinguishable. So what this means is that in 720, we have overcounted by a factor of 6, because for any 3 positions, there are 6 different ways to arrange a 1, 2, and a 3. So we need to reduce this by a factor of 6 in order to get the real number of arrangements that are possible here. Okay, so with this in mind here, for the microstates, let's look at a slightly larger system, because 10 molecules is tiny. Let's say we have 500 molecules, and that 5 of them are going to be dye molecules. We end up with 1,000, million, billion, 255 billion different ways for this to happen. And there are only going to be 46 of those that are ordered where all of the dye molecules are together, are next to each other. So that's the key thing here. So in this view we have here, we would consider this arrangement that we have to both of these arrangements to be dispersed. So the dye molecules are not next to each other. In this case, in the bottom case here, where the 3 dye molecules are right next to each other, we would call that a droplet. So you would see visually there's a droplet of dye, and then the rest of the water looks clear. And so how often does that happen? Well, it can happen here, it can happen here, it can happen here. And if you go through, you find that there are 8 different ways that this can happen, where they're all together. So out of the 120 possibilities, only 8 of them have a state that we would describe as droplet. And all 112 other ones have a state that we would describe as dispersed. So some terminology that's important here. The 3, PowerPoint's being annoying, 3 together we call droplet. Not together we call dispersed. Each specific arrangement that you can come up with here is called a microstate. So there are 120 possible microstates. Each description that we have down here is called a macrostate. And so in the case of 3 of them together, our droplet macrostate, there are 8 microstates. And in the dispersed state, we have 112 microstates. so the idea is that when we have a chemical system and the molecules are in constant random motion because of the kinetic molecular theory, what is happening is that the system is constantly sampling different microstates. And most of the time, it is going to be a dispersed microstate, and only occasionally will it be a microstate that we call a droplet. When we go back to the numbers we just looked at, where there are 500 boxes and 5 dye molecules, then we have 255 billion microstates total. We have 46 microstates that are a droplet, and we have whatever this is minus 46, that many microstates that are dispersed. Thinking about back to our deck of cards, ordered is a type of macrostate, and shuffled or disordered is a type of macrostate. And there are so many more microstates in the disordered macrostate that we will never see the macrostate of ordered come from random shuffling. So this number that we got here is is only 500. A real chemical system. Let's think of a drop of water. How many molecules are in a drop of water? How did you get the 46 droplet microstates? So the idea of the 46 droplet microstates is that if you have all 5 of the molecules together, then there are 46 places within the ordered list of 50 boxes that you can have 5 of them together. How many molecules are in a drop of water? Well, about 1.67 times 10 to the 21st. This is too big a number for even this program I'm using to calculate the number of microstates for. So this number here is just under 2 billion trillion molecules, million billion molecules. So I'm going to take a billionth of a drop of water. A billionth of a drop of water is going to have 1.67 times 10 to the 12th molecules in it. And let's say we have 100,000 dye molecules that we want to be together. Take a look at this answer that we have here, 1.6 times 10 to the almost 800,000. The example we did earlier for the deck of cards, when we had to have the entire universe shuffling cards once every nanosecond, that was a case where we had, let me find my number again so I can type that in for comparison. That was 3 times 10 to the 66. For a real chemical system, this is what we're talking about. So the point, what is the 100,000? The 100,000 here is how many dye molecules I'm saying that we have. I understand people are getting lost from the math here. I'm not going to be expecting you to do this math. The math that I am showing here is to illustrate a point that I am making. The point I am making is that this concept of entropy tells us very precisely how unlikely something is to happen. So we could say we have the gas in the room that you're sitting in. What is the possibility that all of the molecules that are in that gas will randomly show up in a cubic square centimeter up in the upper left-hand corner of your room? And so you're left with vacuum everywhere else. And And there's no physical property of the motion of the molecules that is preventing that from happening. Why doesn't it ever happen? The reason is that it is so ridiculously unlikely that it is effectively impossible, because the chances are so small, is what's going on here. So, and that's the only real point from this. So what that brings us to is a quote from Albert Einstein. A theory is the more impressive, the greater the simplicity of its premises is, the more different kinds of things it relates, and the more extended its area of applicability. Therefore, the deep impression which classical thermodynamics made upon me. It is the only physical theory of universal content concerning which I am convinced that within the framework of the applicability of its basic concepts, it will never be overthrown. This idea of the statistics of what is possible and what is not is the only thing that Einstein thought was so absolutely certain that it's never going to be overthrown. And it's the thing that explains why certain reactions are spontaneous and other reactions are not. And it comes down to the probabilities of the reaction going the other way are just stupidly low. Now, this brings us to the recognition that the numbers that we are working with here are just way too big to do anything with. I mean, 10 to the almost 800,000 is absolutely stupidly impossible to work with. Well, logarithms are able to reduce the size of numbers very, very effectively. Remember how in pH and POH, we were able to take something like 10 to the minus 14, and by applying the logarithm, we turn that into 14. So this law, which is written over Ludwig Boltzmann's gravestone, because he's the one that came up with it, is that entropy, S, equals K, the Boltzmann's constant, times the natural logarithm of W. So this log here means ln, the natural logarithm. W is the numbers that we've been calculating here. W is the number of ways that a system can be arranged within a particular macro state. So it is the number of microstates in a specific macro state. Now, remember what we did when we looked at drawing the first two cards. When we drew the first two cards, the number of possibilities for the first card was 52. The number of possibilities for the second card was 51 because there was one less card we were drawing from. When we found the total number of possibilities, we multiplied those together. So the W for the first card times the W for the second card is what gives us the total W for the pair of cards. But in thermodynamics, we prefer to look at addition and subtraction rather than at multiplication. And that's one of the convenient things about logarithms, is that it converts exactly that. So if we take the natural log of W1 times W2, we get the natural log of W1 plus the natural log of W2. So what this means then is that the Boltzmann formula for entropy, where this here is S equals Boltzmann's constant times this. So what this means is that we are able to not only start working with much more reasonably sized numbers by taking the natural logarithm, we are also able to do thermodynamics calculations using this concept of entropy, using addition the same way that we do addition of enthalpy of a system or energy of a system. So if you have the enthalpy of a glass of water and then the enthalpy of another glass of water that you bring together, then the total enthalpy is the sum of the two. Same thing with entropy. The entropy of one glass of water plus the entropy of the second glass of water is the entropy of the pair of glasses of water. So this means that we are now able to treat S the same way that we treat H in our calculations. Okay, so in practice, we don't tend to use this formula to calculate entropies, just because W is just too stupidly big. But understanding that it comes from this concept helps us develop an intuition about which of two systems will have a higher entropy, and thus which direction a reaction is going to proceed. So we have an example here of dye molecules sitting in a glass of water, and they spontaneously disperse over time. And they don't spontaneously go back into a droplet. And that is exactly what entropy is telling us. Similarly, we know that a gas has many more places for a molecule to go than in a liquid because they're so much further apart. And so if there's enough energy, a substance will be in the gas phase rather than in the liquid phase, because the entropy of that gas phase is so much higher. So this leads us to the second law of thermodynamics, which says that for any spontaneous process, the entropy change of the universe is greater than or equal to 0. Entropy increases, disorder increases. And it does it simply because there are so many more ways for disorder to exist than for order to exist. W is so much bigger for a disordered macrostate than for an ordered macrostate. Now, the problem with this formulation of the second law of thermodynamics is that imagine calculating W for the universe. That's just kind of a ludicrous concept to even think about. But there's some tricks we can follow to, to make this a more tractable kind of problem. And so the first trick is that we divide the universe up into two parts: the system that we're studying and everything else, the surroundings. Now, when we're talking about the surroundings, we don't really care about all of the surroundings. You know, if I'm carrying out a reaction in my beaker and my lab mate a couple spaces down is carrying out a reaction in her beaker, what she's doing in her beaker isn't going to affect what's going on in my beaker. So we only really care about what happens to the surroundings as a result of what I'm doing in my own beaker. And what that means is that we look at the heat transfer. That's the only thing that's going on into or out of my system. It's either exothermic, meaning Q is less than 0, or it's endothermic, meaning Q is greater than 0. So, so now what we mean by the delta S of the surroundings is asking ourselves what effect on the entropy of the surroundings we have when there is a heat transfer to it. Well, let's think about that heat transfer. If we put heat into the surroundings, then now there is more energy that can be distributed amongst the various modes of motion of all of the molecules that you have. And so the ways of arranging that energy in the surroundings increases. And so through a bunch of math that we're not going to go into, we can find that the change of entropy of the surroundings is equal to negative Q over T. So if it's cold, then adding heat to the surroundings has a large effect on its entropy. If it's already hot, then adding more heat to the surroundings doesn't affect the entropy of the surroundings all that much. So we can take these concepts and combine them. One more thing here, Q. Well, what can we do with Q? Well, if we're operating under a constant pressure condition, then the amount of heat that is released is the delta H, the change in enthalpy of the system. So, what that means is that we have now been able to take all of this, this whole thing of the system and the surroundings, and we're able to rewrite it so that we are only dealing with the system. We are expressing the change in entropy of the universe as a change in entropy of the system and a change in enthalpy of the system.
Professor Osman, could you go over all of that again and maybe slow down a little bit?
Okay, so we'll back up. The idea of a spontaneous process, the second law of thermodynamics, is that the universe goes from states of low entropy to states of high entropy. It goes from states where W increases. And it does that because, very simply, it is it is so improbable that it would go the other way that it never happens. We get over the problem of trying to deal with the entropy of the universe as a meaningful concept by dividing the universe into two parts: the system that we are studying and everything else, meaning the surroundings. And by everything else, what we're really meaning is the portion of the surroundings that are affected by the reaction we are studying. So I use the example of, I have a beaker, my neighbor has a beaker, we're carrying out different reactions. What my neighbor's doing in her beaker has no effect on what's going on in my beaker. So the only part of the impact on the surroundings that we care about is heat transfer. So we can either have an exothermic reaction where heat is transferred into the surroundings, or we can have an endothermic reaction where heat is absorbed to the system from the surroundings. What effect does a heat transfer to or from the surroundings have on the entropy of the surroundings? Well, if you put heat into the surroundings, then you now have more energy in the surroundings that can be dispersed amongst the various molecules of the surroundings. And so that increases the entropy of the surroundings. And we're not going through the math to demonstrate that the change in entropy of the surroundings is negative Q over T. But that is the relationship that we have. T here has to be measured in Kelvin. We also noted that since most reactions that we are looking at are under constant pressure conditions, that the heat transfer under constant pressure conditions is the same as the delta H, the change in enthalpy of the system. And so we now are able to write the delta S of the universe as an expression of things that are only relating to the system: the change in entropy of the system, the change in enthalpy of the system, and the temperature of the system. And so now we can relate this to the inequality I wrote up at the top for the spontaneous process. The delta S of the universe is greater than or equal to 0, and write it this way: the delta S of the system minus delta H of the system over T greater than 0 for a spontaneous process. Now we're going to rearrange this a little bit. We're going to multiply through by negative T. Okay. And since we have now gotten rid of all of the annoying surroundings stuff, we're just assuming that everything has to do with the system, we can drop the subscripts. And we get delta H minus T delta S is less than or equal to 0 for a spontaneous process. This is a powerful enough expression that we on the left-hand side that we have a special name for it: the Gibbs free energy, or G. Now, you may remember that enthalpy, H, was a state function. It only depended on the state of the system, not how you got there. S is similarly a state function because it depends on W. It depends on the number of ways of arranging the system. It doesn't matter how you got there. So S is a state function. T is a state function. It's just the temperature of the system. So that means G itself is also a state function. One of the main things that comes from a state function is that you can use Hess's law on it. Now, Hess's law was something that was introduced in Chem 111, but it's been a while since we've done it, so I thought I would go through a reintroduction to Hess's law so that everybody can be on the same page with that. So I am going to bring up another presentation for that. Okay, so we're going to look at an example system. Hydrogen is a potential clean fuel. It's called clean because it doesn't produce carbon dioxide when it's burned. But how do we make hydrogen gas? One way which doesn't look very clean itself is to react carbon with water to make CO2 and hydrogen gas. And to run this reaction, it actually takes energy to do it. Now, 90.1 kilojoules per mole have to be added to this reaction for it to proceed. Notice two things about this. First, the delta H is positive, meaning it's endothermic. Second, the per mole part of this means per units of the reaction as written. So 90.1 kilojoules are required for 1 mole of carbon, but that's also for every 2 moles of hydrogen produced. So the conceptual question you should have at the back of your mind is, if we're adding energy in this reaction, where exactly does this energy go? Well, we know it's some kind of chemical potential energy, but we don't really know what that means yet. We'll get a better idea of that in a little bit. Now let's notice that in this conversion reaction, both the coal and the hydrogen are combustible fuels, which what the reaction we're looking at is converting one fuel, carbon, into another fuel, hydrogen. So what we want to do is look at the two combustion reactions, the combustion of carbon and the combustion of hydrogen, and compare their delta H's. And if we look at those, we can notice something interesting, that if we take this reaction minus this reaction, we get this. So let's think about what that ends up meaning, and let's explore this visually. If we take these two reactions and add them together, where this one here is the reverse of this reaction here, we get this other reaction that we were interested in. So if we have this reaction here, we have the reverse of this reaction, which means we flip the sign of the delta H. We then add the reactions, and then we add the delta H's as we go through here. Now, there are multiple ways to represent this. This is a question of Hess's law. The heat of any reaction is equal to the sum of the heats of reaction for any set of reactions that are, in sum, equivalent to the overall reaction. So let's now express this as a map. So this is something that I call box notation. I take a set of reactants and I put a box around it. I put a set of products over here. We now imagine what happens if we burn the carbon. Well, the carbon and the carbon with the hydrogen and the oxygen can go that way, or they can go that way. Okay. So in this case, we are burning the carbon. In this case, we are burning the hydrogen, and we're leaving the other thing unchanged. So the way to think about this is that we've got two different paths to get from here to here. So we have the fast path, which is just a single step, and we have the roundabout the bend path, which goes this way. And however we get from here to here, the delta H has to be the same both ways. That's the idea of it being a state function. So I want to illustrate that idea of a state function by thinking about altitude. Let's suppose we have a hiker that wants to get to the top of a mountain. She could go straight up the mountain, or she could take switchbacks until she gets to the top. Or she could ride in a helicopter up to the top. Whatever route she ends up taking, though, her change in altitude is exactly the same, because altitude is a state function. This is just like enthalpy. Whatever path you take, the change in enthalpy is going to be the same. And that gives us suggests a different way to visualize the reactions we're using in addition to the two ways we've looked at it before. So we have the chemical algebra way to do it, and we have the box notation way to do it. But we also have the state function method. We have an energy scale. We have reactants, we have products. We have a second reaction. We have reactants, and we have products that you can get from it. And so our delta H is simply the difference between these two lines right that we have right here. All three of these models show you the same thing, and they are based on Hess's law, and it comes just from there being a enthalpy being a state function.
Professor Osman.
Yes.
So if you go back to when you took the negative 393.5 minus the negative 43.6, why didn't you multiply the 486 by 2 since we have 2 moles of it?
So if you look at, I'm going to back up. So if you look at what's going on here, these enthalpies that are shown are for the reaction as written.
Okay.
Okay. And we, when we reversed this reaction and then added them, we didn't divide by 2, right?
Right.
So, so when we take this reaction and the O's cancel and the O's cancel on this side as well, then we don't divide by 2 for these.
So then what would it have looked like had we been multiplying by 2? Because I know in Newton they always have us multiply by whatever moles the...
So are you talking about heats of formation?
Maybe.
Yeah, so we're about to get to that.
Okay.
Okay, so in the chemical algebra method that is I'm describing right here, it is a, we do it based upon the reactions as written.
And those are all constants, right? Those delta H's of certain elements?
No, they are delta H's for a reaction. And this is a critical point that I'm was just about to get to. So, so my computer is acting slow. Stop it. Nuts. Here we go. Okay. So when we look at some kind of reaction we care about, reactants going to products, generally what we want to do is have some kind of convenient intermediates, which will allow us to have this alternate pathway that we're going to. So we have the delta H of the reactants, the delta H of the products, and we have this particular path. And then we can do something like this. Delta H of reaction is the delta H for this arrow, the delta H for this arrow. Now, the question is, what are the convenient intermediates we want to use? So the idea here is that every compound is made up of elements, which means that we can, for every compound, we can write a reaction that forms that compound from its elements in standard state. So the numbers that you, Ashlyn, were just talking about, which are the enthalpies of a compound, they are not the enthalpies of a compound. They are the enthalpy for the specific reaction that we have just written. They are the enthalpy for the formation reaction. That is why when you look at them in the table, they are listed as delta H sub F, the enthalpy of formation of the compound. And so each of these components here, delta H sub F of a species, has a value, but we know that we can, that just given the nature of the compound, we can figure out what its formation reaction was.
Professor Osman, will you slow down just a little bit?
Okay.
And then also, quick question. Are the constants, like the constant delta H's, delta S's, only for standard free energy?
They are for the formation reaction under standard conditions. And by standard conditions, we mean at 25 degrees C, 1 atmosphere pressure.
Okay, cool.
Okay. And you shouldn't think of them necessarily as being constants, but rather as being measured values. Okay. Okay. So the idea here is that our convenient intermediates are going to be elements in standard state. And because the reactant box and the product box contain exactly the same set of elements, then those elements in standard state are going to be the same for both the formation reactions for the reactants and for the formation reactions of the products. Now, you need to think as well about the direction of the arrows, because we are talking about the formation of the compounds from the elements in standard state. And so the arrows, the reaction arrows, go from the elements in standard state to the products and from the elements in standard state to the reactants, which means that when we follow our alternate pathway going from reactants to products, we are going against the arrow for the reactants and along the arrow for the products, which is why our delta H of reaction is the delta H of formation of the products minus the delta H formation of the reactants, because the reactant arrow we're going against and the product arrow we're going with. So it's very tempting to just have this thing memorized as products minus reactants. I recommend not doing that because there are other ways to do it other than heats of formation. So you've all done examples of this. I'll go through that in a minute. Actually, it's worth going through this one a little bit. So this gets to the, darn it, this gets to the question of that you were somebody was bringing up about the multiplying by the number that we have. Here's an example where we have a stoichiometric coefficient of 2 here and a stoichiometric coefficient of 4 here. When we look up the enthalpy of formation from our table for water or for HCl, it is for the formation of 1 mole of it, right? So that's why we multiply by 4 for the HCl and by 2 for the H2O, because the specific reactions we were dealing with were for 1 mole. So if we look down here at the bottom, the formation reaction for H2O is for the formation of 1 mole of H2O. But when we're adding things up here, we have to double that reaction in order to get the 2 moles of H2O that we need. And it's negative because it needs to be on the reactant side rather than on the product side, which you have here. And so if you write up all of these reactions, all of the elements in standard state just cancel out, and we're left with the overall reaction. So, and the way to think of this is by using this box notation and thinking of the formation reaction as going from elements in standard state to the reactants and to the products. And that the path you're following is this, this curved arrow here, so you're going against the arrow for the reactants and with the arrow for the products, explaining the signs. Okay. So the things to remember are that the compound that you're talking about, whether it's on reactant or product side here, in the formation reaction is always the product. In the formation reaction, the product is always formed, 1 mole of it's formed. The states of matter matter. So if it takes more energy to form a gas phase product than a liquid phase product. When you follow these rules, there is only 1 valid formation reaction for any compound you're dealing with. Now, so this is just now summarizing the example I was just using. Elements in standard state are our convenient intermediates. There are other possible types of intermediates though. Maybe instead of formation reactions, you are told to use combustion products, because in this reaction, this compound could be combusted, could be burned. This compound could be burned. This compound could be burned. The combustion products are going to be the same, but notice that if you're using combustion reactions, the arrows go the opposite direction from the formations. So in this case, if you were using combustion reactions instead of formation reactions, it would be reactants minus products instead of products minus reactants, which is why I strongly recommend do not just memorize products minus reactants. Think about
why are the arrows going different directions?
Because in this case, the fundamental reactions we were using was the formation reaction of the reactants and the formation reaction of the products. So we are forming the reactant from the elements in standard state. That's what we mean by a formation reaction. In this case, we are talking about a combustion reaction where we take our compound, we react it with oxygen to form its combustion products. And so the reaction arrow goes from the reactant to the combustion products. So you think about what the reaction actually is. And so there's a comment there's a comment here that says rushing through this material is making it difficult to absorb. The problem here is that this is not new material. This is Chem 111 material, and I'm doing a review of it right now. Okay. The point of all of this was a review of Hess's law to show you how you go through the various calculations for enthalpy. And the idea is that you can do exactly the same thing for entropy and exactly the same thing for Gibbs free energy. When you look up your these values in the back of a textbook or on the internet, you will find your delta H's of formation. And so notice the subscript F here, meaning that this is the enthalpy change for the formation reaction of this compound. You have a delta G of formation, which is again the Gibbs free energy change for the formation reaction. And we have the standard entropy of the compounds. Now, notice that this one does not have a delta in front of it. That is because unlike enthalpy and Gibbs free energy, entropy does have an absolute zero value. If you imagine taking a perfect crystal at 0 degrees Kelvin and think about what W will be for that system, W will be 1. There's only one way to arrange every piece of every atom that is in that system in a perfect crystal with no energy in it at all at 0 degrees Kelvin. The natural log of 1 is 0. So a perfect crystal at 0 degrees Kelvin has an entropy of 0. That is the third law of thermodynamics, which means that instead of having the delta S for some reaction, like the formation reaction, what is tabulated are the absolute entropies of the substance at that temperature, 298 degrees K in this case. In all of these cases, you can just use Hess's law to figure out delta H, delta G, or delta S. Now, usually what we care about, we won't use typically delta G's from tables like this, because if you remember back here, there is a temperature dependence to delta G that is stronger than the independent temperature dependence of delta S or delta H. And we use that to determine whether something is spontaneous or not. So remember that our criterion here, delta H minus T delta S less than or equal to 0, means that it's spontaneous, which means negative delta G is a spontaneous reaction. Positive delta G is a non-spontaneous reaction. Another way to say that is that it is that the reverse reaction would be spontaneous. If delta G equals 0, then that means that the reaction is spontaneous both forward and backward. So it is in equilibrium at that point.
Professor Hoffman?
Yes.
Could you describe the relationship? So it's like if delta S is greater than 0, it's spontaneous. Can you describe that relationship to the delta G as well and how they compare?
Right. So, so actually I was about to do that. I was about to show this slide right here. And so the rule is delta G greater than 0 is non-spontaneous. Delta G less than 0 is spontaneous. And delta G equals 0 is equilibrium going between them. If we have delta H less than 0 and delta S greater than 0, then both of these terms are negative, and so this reaction will always be spontaneous. If, however, delta S is less than 0, then this term is positive, this term is negative. We have a straight line, and so at low temperature it's going to be spontaneous, at high temperature it will be non-spontaneous. And then swap the sign of delta H, and we have the same kind of things going on here. And that's it for the new material for this week. I do strongly recommend reviewing for yourself Hess's law so that you are very comfortable with it, because applying Hess's law to delta H and delta S is part of solving the problem for delta G. And this equation is always true when the tabulated delta G of formation values are at a given temperature, which means if you change the temperature here, it's not going to work. So delta H and delta S don't depend on temperature nearly as much as delta G does. Okay, so I know I've run us out of time. Thank you for listening. For any students that want to stay after class and ask me some questions, that's fine. I'm happy to do that. So I will plan on doing Q&A and any review on any of these materials that are necessary on Wednesday and Thursday. Tomorrow's class is going to be essentially a duplicate of today's class. So I'm not expecting students to attend classes they weren't signed up for. Thank you very much. We'll now move to any questions people want to ask after class.
Okay. So, when you were talking about the microstates and the map that you're doing to that, I just wanted to clarify, when I was reading the book notes, it talked about final versus initial W, and then you talked about solving for W, but it was always given to us. So
you were given W's, you mean?
Yeah, we were always given W's. And then when you were doing the math, you were like, well, we need to solve for it. And I was like, oh, well, they didn't tell us how to solve for it.
Right. So I am not going to be asking you to calculate any W's.
Okay.
I know I spent a long time on that part. The point of going into all of that was so that you could get a sense of, even for a system as small as a deck of 52 cards, how ridiculously large the numbers that you get for W are, and how impossible it would be for you ever to have a randomly shuffled deck end up being in order. And that motivates why we are able to take something like a mole of something, a chemically relevant amount of something, and say, yeah, what statistically, it will always go to the system of higher entropy.
Okay. Also, more of a logistical question. Would you consider, so since we have these 10 sections for this next upcoming test and then the final, and because you had to deal with all the meetings about cheating, would you consider not having the group assignment, the last one?
The thing is that I think the group assignment is likely to help with understanding this material. It's not something over on top of it. It is something that is going to get you to understand better how this material works together. So I think it's to your benefit to have it.
All right. What was my other question? And then can we just go over again the difference between when you're multiplying by the moles solving for that delta, what is it, delta G or delta S, one of the two, versus when you're not multiplying by the moles?
Sure, absolutely. So in every case, let me share screen again and call that up. Excuse me. Sorry, my brain hit a speed bump. I'm trying to, here we go. All right, so taking a look here. So let's look at the bottom right here, the bottom part at this point.
Okay.
This is what I call chemical algebra. So
Right.
we have a reaction, we have another reaction. If we add them together, meaning we take the reactants and we take and put them all in, we take the products, we put them all in, and then we figure out what's on both sides and cancel them out. Whatever the delta H is for this line, whatever the delta H is for this line, you just add them because you're just adding the reactions. You don't look at stoichiometric coefficients at this point because you're adding one of this reaction and you're adding one of this reaction.
Okay.
Now, when we get down to the standard heats of reaction, the standard enthalpies of formation and such. So I want to come to this one here, I think. Let me, okay. So we're given this reaction and you look up the delta H's of formation for the various components.
Right, and it's in standard conditions, correct?
Yes. Well, delta H of formation means that it is the delta H for these reactions. We put the elements in standard state on the left-hand side. We put 1 mole of this compound on the right-hand side, and we just make it balance. And this is the delta H for that reaction. So when we then take this information and apply it to the reaction we have here, we need 4 of this reaction in order to get 4 moles of this up here.
Right.
So if we look at this one, this reaction here is this reaction backwards. So we take this and change its sign. This one is this reaction twice and backwards. So we do -2. This reaction is this reaction forwards, so we just take the delta H. This reaction is this reaction 4 times, so we take the delta H formation times 4.
Right, and then just to double check, where did you get, or what, not where did you get, what are those on the bottom left, what are those reactions?
So all you do is you say TiCl4, I'm gonna write that down. If I now take the elements in standard state, Ti, that's a metal, so that's a solid. Okay. Cl4, well, its element in standards, sorry.
No, you're good.
Cl4, well, chlorine in its standard state is Cl2. So to balance it so that I have 4 chlorines on the right, I need 2 Cl2s on the left. And its standard state is gas, so it's a gas. So for every element, every compound you write down, you separate out its elements, you write them in standard state, and you balance the stoichiometry so you get 1 mole of the thing on the right.
Okay.
So the fact that you are now multiplying by 2 for the stoichiometric coefficient comes from the fact that we have defined the formation reaction to be the formation of 1 mole of the compound.
Okay.
Does that help?
Yeah, that makes more sense than earlier. I'm sure if I work with the equations more, it'll make better sense.
Okay.
Awesome. Okay, thank you.
You're welcome. Anybody else that's still here have any questions for me? All right. Thank you all very much.